Recording in progress.
Okay, so good afternoon, everyone. I hope that you are ready to study again. Okay. Let's study today the chapter 6 on univariate time series modeling and forecasting. Okay, so we switch to a new topic, time series. Okay, give me some examples of time series. Okay, you go to the stock market and you collect values over time or the price every day or the stock index every day. You get an example of the time series. Okay, so time series is very common, very common. Here you have some other examples. It's a bit strange. Okay, I have another example. You can see on the slide. What is it? Which is the number of passengers from the specific international airline company. Okay, so on the slide you see an example of time series. What is it? It's the number of passengers of a specific airline company over time. So can you give me some features? What can you observe from the curve? What special can you observe from the curve? So here it is a time block, number of passengers over time. So in 50, 51, 52, 60, for example. Okay, what can you observe from this curve? Okay, any special remark on this curve? What can you observe? Oh, increasing, right? Okay, when you say increasing, what does it mean? Is that okay? You can imagine, right, that you have something like this. Okay, something like a straight line. Okay, not exactly a straight line, but very close. Okay, and then you see that it goes up. Okay, so what does it mean? It means that you have an uptrend. Okay, first of all, the data set has the trend, and then the trend is up. Okay, sometimes you have something going down over time, then you have a downtrend. Yeah, uptrend. Anything else? Number of passengers of a specific airline company. So you can think of Vietnam Airlines, right? Vietjet and so on. Okay, so in a year, in which month you expect more people to travel? In the summer, in the winter, or any specific time or month when you expect more people to travel? Yeah, okay, so okay, why not summer, right? And then you can check actually. So in each year, for example, 50 to 51, okay, you see they have a peak. Okay, around the summer, so a peak around July or August. From 51 to 52, the same. You have a peak somewhere here. Okay, this year the same, right? So somehow you have the what you call seasonality, the same pattern. Okay, over time. Okay, same pattern. For example, you expect the values to increase in the summer each year. Okay, so seasonality is the second remark that you can observe. Okay, so again, when you look at this time plot for the number of airline passengers, first of all, you see the uptrend. Uptrend, the values tend to increase over time, and also seasonality. In the summer, every day, every year, right? Every year, actually, the values tend to be higher. Okay. So this is the first example. The second one, okay, a bit less. Okay, less obvious. So I think that is the S&P index. That's the index. Okay, so it is less obvious. Maybe you need a longer time period to observe something more interesting. Okay, it's about the index, and maybe the return will be better. Again, so these are some examples. You can collect data and can draw a lot of different curves. Okay, so by definition, time series is the collection of observations, values over time. Okay, you can collect values every day, you can collect values every week or every month, every year. Okay, for some macroeconomic variables. Okay. Okay, and the objective of the time series are not this. will be possible to describe. Very often we start with drawing the curve, right? Okay, giving the plot, in this case, the time plot. Okay, so also give the summary statistics, the mean, the variance, and so on. Okay, and all graphical methods. More specifically, time plot to look at that and then to start to observe. The next to model, you're trying to give the best. Okay, somehow again the best fit model, you can call it like this, or the most suitable model. Okay, that you can find to describe your data set. Okay. Okay, so at this level, we may have several approaches. Before you learn about CRM, classical linear regression model. Okay, before up to now, we learn about CRM. CRM, what is it? When you explain the variation of y using x variables. Okay, so before CRM, let's take the easy one, y equal to alpha plus beta x plus u, okay, over time, because we talk about the time series. Okay, then it means that we try to explain the variation of variability of y using x. And it corresponds to which model? Which model? I think the second one. Structural model, because you use the present of past values of other variables to explain the current variable. Okay, for example, you are interested in this y variable. Okay, CRM will help you somehow explain why using the values of other variables. Right? So it's not okay. Okay, sometimes you may also add the lag y and so on. Okay, but there's another extension. So it belongs to what we call the structural model. Okay, structural models using the current and past values of other variables to explain the current value of the variable y of your interest. Is that okay? So structural model. Okay, but it's not always possible. Why? Because sometimes X data set is not available. Sometimes X and Y do not have the same frequency. Okay, if you have here Y daily, not one monthly or yearly, then maybe it's not the best one, right? Okay, okay, for some reason, it's not always possible. Okay, then univariate model is the second approach. Univariate. Okay, univariate model is another approach. When you try to explain, right, yt using the past values of the same variable. Okay, so imagine that now I try to give a model with yt here. Okay, on the right hand side, you have yt minus 1, yt minus 2, and also u terms. Okay, okay, which is what I call the univariate model. So, time series model. Like okay, as you see today, right, AR or alpha or MA or combination of both. Okay, so univariate models. Okay, it's also possible to combine both. For example, when you have a system, okay, of equations, we call the VAR model, vector autoregressive model. Okay, okay, or combination of both. Okay. Structural and univariate models. Okay, for example, vector autoregressive model, VAR. Okay, when you have a system of equations, in this case, you put your variables. For example, you have y1, y2, okay, up to yn all together at a time t, and you try to explain it using the past values of the vectors. Okay, then we somehow have the combination of both structural and also univariate models. Okay, okay, so in this case, we rather have a system. Okay, so for modeling, So again, you have a structural model approach or univariate approach or the combination of both. Okay. Like a vector autoregressive model. Okay. Okay. So in this chapter, we rather focus on univariate models. AR, MA, also combination to get ARMA models, ARMA models. Okay, so after getting the best fit model, you can use it to forecast. So we try to forecast, okay, what is the stock return the following days? Yeah. Sometimes you have a low volatility models, okay, with more advanced time series models, okay, to estimate the future values of the series. Yeah, what do we predict for the next values? And finally, to control. Okay? So you're trying to intervene in the whole process, to take action to intervene. Right? That's what we call it a controlling step. Okay. Okay. When you try to intervene, so that it gets some kind of reaction and feedback from the system. Okay. Clearly, time series and forecasting has a lot of application. Okay, in economic, especially economic planning, sales forecasting, inventory control, budgeting, and financial risk management. Okay, risk management, you have a lot of volatility models. You also need to combine sometimes models for the return and also volatility. Okay. So which are the basic concepts you need to know? Okay, a time series, when you talk about the time series, as we saw right, from the example, you can see the linear trend. Is that okay? You can also see the seasonality, the same pattern to repeat every day. Is that okay? Okay. So my question is, okay, suppose you have the trend like this, how to lead trend? How to lead trend? Okay, often the models we talk about later, okay, they will for stationary process, or stationary series. Okay. So time series. Maybe we can show you again the examples before. It has a trend. Okay, this one clearly has a trend, linear trend, and also seasonality. So my question is how to lead trend? How to lead trend? It means that how to separate the trend. Right up here, time series. Okay, so the first component that we can observe from the curve is the linear trend. Okay, so how to understand the linear trend means that higher value of t will give you a higher value of y, okay, the variable of your interest. So in order to detrend, we can do what? How to detrend a series? Okay, but not enough. Not enough. So this is trend means that you have a component, something here. You have a t axis, right? The values tend to increase over time. So when you take it, okay, minus the mean, right? So it's a constant. Okay, still. Okay, so okay, the what? Yeah. Okay, so I see your idea. But in this case, you have to regress, right? So somehow we regress yt. Against the t variable. Is that right? And then you minus, yeah, that's correct. That's that now. Okay, then you have the remaining part. Okay, the remaining part, which is the series, which is already the trend from the original one. So it means that you can take right, the series values you regress, like a running in the linear regression model, okay, against the t variable. Okay, then you can get alpha beta coefficient, and you take this minus that one. Okay, so the remaining part with the dots here means the series already the trend. Okay. Okay. Because with the linear trend, sometimes we allow you to keep the linear trend with some others. Okay, better to remove that before or separate before. Again, how about the seasonality? Like here you see the number of centers every year tend to increase during the summer, like in July, right? There's more seasonality. How to remove it? Okay. Requires it. Okay, any idea? So seasonality. Okay, for example, one okay, we may have other types of seasonality, but of course it should be like regular, okay, so that it can somehow separate it. For example, every year, right? Yeah, have you heard of the January effect? January effect for the stock market. Okay, you can search right in the literature. January effect. Stock return tend to be higher in January. Okay. Sometimes people may also investigate the Friday effect. I don't remember Wednesday effect. Yeah. So along specific days during the week. For example, we have a higher value in July or every year. Okay, means the same pattern to repeat every year. So how to separate it? Have you ever seen that before? July. So I mean, okay. Not okay. Regression, but in this case, maybe it's better you take the difference. Okay, you remember the first difference. Maybe it is related to what you say. But in this case, it's better to take the first difference. Consider the first difference. Okay, if you have a monthly data, then you can take yt minus yt minus 12, the value 1 year before. So there we go. So what about daily data? Daily data, so daily data. Okay, so if you have a 250, so how many days do you have? So 365, right? So you take yt minus yt minus 365. Okay, so if you have a quarterly data, then you take yt minus 4. Is that okay? So taking into account the seasonality. Okay. Okay, and so after the trending, right? The trending after removing seasonality, then the remaining part may work well with the models that we discussed today. Part. Okay, we may have some kind of seasonality, but then it's easier to control. It's easier to control, and it's easier to look at. Okay, after removing linear trend and after removing seasonality. Okay. Okay, so again here take yt minus 12 with the value 1 year before. Right? So in case you have daily data, in case you have quarterly data, then you adjust. Okay? The idea is to take a difference, okay, compared to the value 1 year ago. Okay. So first of all, the first important concept is about the stationarity. Stationarity. Time series. Set to be stationary when? Stationary. We have several. Hả? Các bạn rõ rồi, phải nhìn vào đây. Chứ cái máy của cô, có kìa. Các bạn không thấy hả? Ở đây là cô mở rồi đấy nhá. Đấy là hay là nếu không cô để đây, không biết bạn nhìn rõ hơn không? Tại vì cô nghĩ cái này có Này là ok, cái này là cái của cái máy này của cô không giúp thì thêm, chỉ là nhìn thấy tổng thể thôi, tức là do cái này đúng không? Mấy tuần trước bạn nhìn rõ không? Hôm nay cái mic nó hơi khác một chút, đúng không? Vẫn thấy đúng không? Đấy là do cái này ạ, do cái này chứ không, cô không chỉnh được cái này là do trường xếp. Cô chỉ để cái này để hỗ trợ thêm.
Ý là cô để cái góc hôm bữa cô nói nhìn nó bao quát, còn cái góc hôm nay nó bị khuất một xíu đó cô.
Không, cái gì nhỉ, cái camera cái này đúng không? Camera của trường này nó cố định luôn rồi ấy.
Không, cái camera của cô.
Cô hả? Tức là tóm lại nhá, bữa trước là cô hay để ở góc nào để nhìn lại tức là vẫn có thể nhìn được cái camera của máy cô đúng không?
Dạ đúng rồi cô.
Ok, tức là em muốn nhìn thấy bảng hay là em muốn nhìn thấy
cái bảng đó cô, tại vì cái camera của trường nó bị khuất ấy.
Ok, rồi thử camera của trường thì nó được một góc, cái nào cũng được một góc cả, thử đóng thử cái này. Tại vì hình như là đây là cô share rồi mà đúng không? Cô share video rồi đúng không?
Đúng
Sao
rồi.
nó không được nhỉ? Bình thường là tức là hiện tại là bạn có thấy được không?
Dạ thấy á cô, nhưng mà là nó bị khuất góc thôi, nó không được quát cái hôm
cái gì luôn á.
Dạ rồi được rồi đó cô.
Được rồi, bây giờ được rồi. Tại do từ đấy gì? Từ đây nhìn nó không nhìn thấy gì luôn, không biết là. Ok, ổn hơn không?
Dạ rồi á cô. Em cảm ơn.
Ok. Nói chung là ai mà học online thì bị phạt đúng không? Không, cái phòng này nó còn đỡ này, có một số phòng nó còn tệ hơn. Buổi đầu tiên các bạn còn chẳng nghe gì. Ok, đây hình như là bắt đầu cô có thấy rồi. Này vẫn là cái của trường. Hình như nó bị lệch đúng không? Camera của trường nó bị lệch đi một góc. Bên này thì thấy đúng không?
Dạ.
Cái này thì nó bị mất đến đây.
Dạ đúng rồi.
Đúng rồi, phòng vậy. Thôi biết vậy. Thôi thì tạo điều kiện cho các bạn thôi, xin biết sau. Ok. Then the series is said to be stationary. Okay, strictly stationary when the probability measure for the sequence yt is the same as yt plus or minus m. Is that okay? So probability of this event is the same as probability of the same event with yt plus m. Okay, but an easier concept of stationarity that we call weakly stationary is easier to work with. Okay, the series is said to be weakly stationary when it has a constant mean. Okay, constant mean, constant variance, and constant autocovariance for a given lag. Okay, so I hope that you see the last part of the slide. Okay, so we mainly used the weakly stationary series.
Is it strictly stationary process? Is there any series that have the strictly stationary process?
Strictly stationary process.
Is there any series that?
I think that we work with this one more often. Okay. Okay. So that one I think it will be more theoretical. But if
theoretical, do we have any series that have property?
If you give it, then it should be. But if there is anyone, okay, if there is any way to check it or not, okay, okay, there is something that we have to think about.
Constant series is a strictly stationary process.
Yeah. So in this case, yeah. Yeah, for some of them, right, it's very easy to check, but for others, I think that the second concept is much easier to check. Okay. Okay, so the series is said to be stationary, okay, and weakly stationary. Sometimes they call it covariance stationary when it has constant mean, constant variance, and also constant autocovariance. Right? Autocovariance because the covariance is generated from the same series, okay, for a given lag. The weekly stationary, okay, or covariance stationary, when it has the constant mean expectation YT to be equal to a constant. The mu variance YT also equal to a constant. Okay, variance, which is expectation y minus mu squared, okay, and we call it sigma squared. And finite, okay, constant variance, and this is a finite number. Okay, and the next one is the what we call the autocovariance, covariance of YT minus mu. Okay, and so either you use the expectation or covariance. Maybe I write out with the covariance. YT. Okay, you can write out with minus s or plus s. I think that here we okay, we use the T1 and T2. Okay, okay, but in practice you can write out with T or T minus or plus s. Okay. So to use the same operation, I will use plus s, where s is the lag. S is the difference between T1 and T2. Okay, 2 points in time. There is the constant depending on S only. Okay. Okay. And it is what? It is the expectation. That's the expectation. Covariance, we call it autocovariance, which is equal to expectation of YT under the first assumption. We know that. What is it? Expectation of YT is mu, so we have mu times YT, okay, like this, plus S minus mu. Okay, to be a constant depending on the lag S on the difference between the 2 points in time. Okay, and we call it autocovariance. Autocovariance. Okay, so just like the variance and covariance, right? You remember we have a correlation coefficient. Okay, now we can also standardize the autocovariance to define what we call the autocorrelation. Okay, so we define autocorrelation. Denoted by tau. Okay, so tau s, by definition, it is simply gamma s divided by gamma 0. Okay, so what is the gamma 0 again? Gamma 0. Gamma 0 is the covariance between YT and YT, okay, which is the variance of YT. Okay. Okay, and then gamma 1, okay, divided by gamma O will give you tau 1. Okay. Okay. And this way we define actually the autocorrelation. Autocorrelation coefficients or autocorrelation. Okay, and then you can also prove that tau s, just like the correlation coefficients, is a number from -1 to 1. It's given there or not? -1 to 1. Okay, so it's a number from -1 to 1. Exactly like the correlation coefficient. Okay, and all the values tau s, yeah, when s equal to 0, 1, 2, 3. Okay, we can constitute autocorrelation coefficient or function ACF. Okay, so you have probably saw that at some point. Autocorrelation function ACF or colonogram. Okay. Okay. ACF, okay, A for autocorrelation, okay, function. Okay. When you put all the values of tau together. Okay. So you see, okay. So what is the value of tau 0? Tau 0, tau 0, gamma 0 divided gamma 0 equal to 1. Yeah. Okay, and the others will vary between -1 and 1. Okay, so we have an example there. The first value tau 0, tau 1 negative, tau 2, 3, 4, 5. Okay, all of them are 0. Okay, an example of ACF. Okay, then the white noise. White noise. Why you need to know about the white noise? Because in any model you have an error term. Okay, and often we want the error term to have the white noise structure. Okay, white noise. It is an example when you plot. Right. So what is a white noise? It's a completely random process or purely random process. So it has no special structure, has constant mean, okay, which may be constant, okay, not necessarily 0, but of course for the error terms that will be 0. For the constant mean or expectation, constant variance. And how about the autocovariance? Autocovariance must be 0. Okay, for the white noise process. Okay, so in this case, the ACF, the white noise process, okay, will be equal to, because the autocorrelation is equal to 0 all the time. Okay? Except s equals to 0, s equals to 0, of course, you get the variance. That's why it's together, not 0. Okay, so ACF of the white noise process, we have only the value 1 when s equal to 0 and 0 everywhere else. Okay. Okay. So what important is the next part. In addition, okay, in addition is if the series is normally distributed, then it can be proved that the tau hat, what is the tau hat s? Tau s is the autocorrelation, all right? The tau s hat is the sample autocorrelation. Okay, that you calculate from the data set. Okay, of course, from the data set you can calculate what you can calculate the sample mean, sample variance, sample standard deviation. Okay, have two series, you can calculate the sample covariance. All right. So, and from the sample covariance and the sample standard deviation, you can get the sample autocorrelation. Is that okay? So that's why I have a tau hat. Okay, and then okay, from the previous papers results, okay, I already saw the paper, it's a very long paper. Okay, then tau s hat will approximately follow the normal distribution with mean 0 variance 1 over t. Okay, where t is the sample size. Okay, and tau s hat again denotes the autocorrelation lag s. Okay, and why it is important, why it is interesting, because when you know that this one follows the normal distribution, then you can get the confidence interval, okay, helping you to test whether tau is equal to 0 or not. Okay, because imagine that later on you have a model, right? So you get the error terms. So again, you need to check the diagnosis test. You want to check that the error terms follow the white noise process. Okay, then in this case, we check if the tau s is equal to 0 or not. By definition, the white noise process will have a tau to be equal to 0. Yeah, autocorrelation gamma s, it will give you tau s to be 0. So later on, you want to test the hypothesis that tau is equal to 0. Okay, to make sure that your error terms in the models of the white noise process, yeah, or white noise structure. Okay, so how to write down then? So in case you want to test tau equal to 0, okay, which is given there, for a single test tau s equal to 0, then you can refer to the confidence interval. Right? Okay. Can I clean the board? Okay, so you have to follow the normal distribution in this case. Okay, then tau s approximately follow the normal distribution. Zero mean variance on t. So what is the 95% confidence interval? How much? What is it? So you get it again, right? So yeah, for example, if you write down, what is it? Oh, t, right? Oh, and 0, 1. Yes, so 95% confidence interval. It'll be around 0 for sure, and 0, 25. 0, 0, 25. 0, 0, 25. Okay, I'll give you here. I think that the critical values will be 9.96. Okay. So the confidence interval will be 0 plus minus 1.96 times standard deviation. Okay? Just like the one you got, you remember for the t-test for your midterm exam, you take the mean plus minus z4 times standard deviation. Okay? Standard deviation is 1 over root t. Okay, so that's why you get plus minus. Okay, plus minus 1.86 divided by root t as the confidence interval. At 95% confidence on level. Okay, so we can use it to test HO tau s equal to 0. Okay, so how to test it? So in case you have, the tau hat s equal to a value beyond this interval, then we reject or not reject. Check or not reject using confidence interval plus minus 1.96 divided by OT. Okay, so what do you think? So I get my confidence interval. If ST tau S, okay, is outside this interval, we can reject. Okay, I show. When it belongs to the confidence interval, we do not reject. I show. Okay, so it's a way to conduct a single test. Tau equal to 0. Then I use simply the confidence interval. How about the case when you have the joint test? Okay, joint test. So again, for the white noise process, all the tau are equal to 0. For S equal to 1, 2, 3, 4, 5. So we missed it. But often you want to look at the joint test to check whether tau, okay, all of them are equal to 0 for certain values of S. Okay, so which ones are available? You have two versions of the test. Okay, they say the second one, okay, John box is better, especially for small sample size. Okay? So the first test based on Hill statistic, the recounted box and PS test. Okay, what is it? So it's very easy to calculate. You take t times the sum of all the tau k squared. Okay, tau k is given from the sample. Okay. Okay, and the John box statistic, which is a different test, you calculate it using this one. Okay. So have a different formula for the test statistic, and both of them follow the chi-square distribution with m degree of freedom. So what is m? M is the number of restrictions in HO. So in case your test, okay, m is the number of restrictions in HO. So here you have tau 1, tau 2, and tau m. So in case you have m restrictions, the test statistic will follow chi-square distribution with degree of freedom equal to m. Okay. Okay, so the second one, in this case, joint test is more convenient. Okay, we can take a look at this example and compare the results. Okay, suppose that we got the 5 sample integration coefficients. Okay, and the values are given there, 0.2. So you can see that it's tau 1 hat. Okay, hat because it's calculated from the sample. Tau 2 hat, tau 3 hat, 4 and 5. Okay. So first of all, we want to test each of them equal to 0. Okay, so in this case, you can use a single test based on confidence interval. Okay, and next, you can use the joint test. Okay. Okay, so how about the first single test? Single test now is easier because you know the confidence interval. So you can check what is the confidence interval. So I have replaced. Okay. You have how many observations? T equal to 100. Okay. T equal to 100, then we get, in this case, the confidence interval is plus minus 1.96 divided by 10. Yeah, root 100 is 10 equal to plus minus 0.196. Okay. Okay, so can you tell me which one is significant, which one is not? Okay. Okay, now we can go again, 0.196. Okay, clearly. Question A, to test each tau s equal to 0 or not, right? Using clearly tau s hat. Okay. First one, 0.207. It is outside the confidence interval. Okay, so clearly the first one is significant. Okay, the second one, minus 0.0013. I think it's very close to 0. So it belongs to the confidence interval, so we do not reject HO. Okay, the next one also small. Next, okay, I think the next 4 values are very small. Okay, maybe do I need to write down anything? So clearly, yeah, only tau 1 hat equal to 0.207 is greater than 0.196. Okay, so this one does not, okay, you can say does not, okay, lie on the confidence interval, does not belong to the confidence interval. Okay, at 95%. Okay, so we can reject HO for tau 1. Then again, how are the others? For the others, we cannot reject. Okay, so they are not significant. Only the first one is significant. Yeah, right. Okay, how about the joint test? Joint test. Okay, I'll show you the calculator. Okay, use the formula and we get the 2 test statistic. 2 test statistic. First test will give you the test statistic to be equal to, for checking. Now it is the joint non-hypothesis. Tau 1, tau 2, 3, 4, so 5. Okay, they are all equal to 0 or not. And then using the first test. Using the first test, Q equals to something, right? Then if you use your calculator, you check that it's 5.09. Second test, joint test, use formula, and you get regime of 5.26. So this is the next step. You compare with the critical value obtained from the chi-square distribution. Okay. With 5, 1, 2, 3, 4, 5 degree freedom. Okay. And 0.005. The area of the right tail. Okay. Okay, so you can open the chi-square distribution. Okay, I suppose you know how to check the critical value. Okay. Okay, so you see something okay, a little bit special, right? Yeah. So in this case, you get the same result on both tests. Yeah, not a reject. Yeah, is the conclusion. Here I think it's 11. Right? Okay, critical value is 11.07. Okay, but your test statistic. Okay, you can use either. Okay, for example, the second one better. 5.26 test statistic is here. 5.26. Okay, so what is conclusion? So TS belongs to the rejection region, does not belong, okay, to the rejection region. Why? Because of 5.26 smaller than 11.7. Yeah, what does it mean? Yeah, not reject.
So why one is significant?
Yeah, so you see, it's the reverse special case, right? Because they don't give you the same, not exactly the same result. Okay, from the first test, okay, you see the tau one is significant. Okay, what's the second test, which is a joint test? Okay, we tell you that, okay, they don't have enough evidence. Okay, so try to remember that when you do not reject HR1, it means that we don't have enough evidence to reject it. So somehow we have to accept it, but it doesn't mean that we prove HR no. We just don't have enough evidence to reject it. Is that okay? So in this case, you get different results. Okay, so what is the reason? What is the reason? If we look at the values, you see that the first one is okay, somehow bigger than or something, right? Okay, but how about the others? The others are very, very, very small. Okay, so when you conduct a joint test, somehow you dilute all the values together. Okay, one of them is larger, but all the others very small. So on average, okay, they are rather small. Okay, so this test doesn't detect okay, the fact that one of them is significant, okay, and not others.
So in practice, what would you take in the
Anyway, you see the first one very well. We use both in practice. Okay, because you know that really that's statistics and data analysis you have to deal with, right? Okay, try to do the best from okay what is available, right?
So imagine you in practice you have to test what is at a different result. So which test do you have more?
So in this case, which one do you think is better?
I think B.
Why B is better? Okay, why not? Okay, B is also good, yeah, because it's very convenient, right? When you test all of them at the same time. It saves a lot of time, of course. But here clearly, tau one half is larger than 0.19. So clearly, the first one is significant. Okay, but the others are not significant. But okay, so which one is better? So in my opinion, I think that is this. The first one is still not significant. Okay, but the fact that you dilute them more, of course, you save time, but you have to pay. Okay, somewhere else. Okay, you have to pay somewhere else because you never okay get everything perfect at the same time. No. Okay, you always okay, in practice, it's like multi-objective, right? Optimization, maybe you already learned. Okay, decision making and so on. Okay, you have to deal with a lot of factors and try to find the efficient solution at some point. Okay, okay. So which is the reasonable solution? Okay, doesn't mean that it's better than all the others. Okay, for any criterion, right? Okay. So somehow you try to find something reasonable. That's it. Okay, so again, I think it's a very interesting example. It doesn't say that okay, the first one is better or the second one is better, but clearly here, okay, the fact that we use the second test, okay, saves a lot of time right? Because you have a joint test. Okay, however, you have to pay for something in the sense that tau one is significant from the single test. Okay, but you cannot detect it from the second test. Okay, so this is one remark. Okay, it doesn't mean that you cannot use the second test. No. Okay, in practice, you can use everything. Okay, but you try to get information as much as you can. Okay.
So John Moss and Foster Pierce, which is better?
Okay, they say the second one is better. So they say that especially for the small samples. Okay. Okay. But I think that very often you get the similar results. Okay, but very often in econometrics and statistics have several tests. Okay. Okay, no more questions. Okay, now let's start to learn about the first family of time series, the called the MA series. Okay, as you know about MA already, moving average series. So the series YT is set to follow a moving average process of order Q denoted by MAQ1. Look at the model YT, you have constant plus the UT from the white noise process. White noise process. So it's like the error term is zero mean. And the linear combination of the lag, okay, lag 1, lag 2, up to lag Q terms. Okay. Okay. So U comes from the white noise process. Okay, so we're saying that now the YT series to follow the moving average process of order Q. Okay, if YT has the following order. To start with the constant mu plus the UT term. Remember that here the coefficient of UT is 1. Okay. In the linear combination of lag UT. To start with lag 1. Yeah. Lag 2 up to lag Q. Okay. Okay, Q is the order of the moving average model. Okay. Okay, where also have to say what is UT. UT is already given. Yeah, okay, right. UT is the white noise process with zero mean. Okay, so expectation of UT is equal to 0. Okay, for the white noise, expectation can be a constant. In this case, it's 0. Okay, because you have one error term. Okay, and for the variance, of course, is a constant. You can call it sigma squared. Sometimes we give the sigma u. Okay, okay, and we call later when I need it, I write down. Okay, very often we call the variance ut to be sigma squared or sigma u squared. Okay. Again, you might wonder what is the expectation variance in covariance. I'm gonna check it. You can see it from here. So then, I would like to check first of all expectation of YT. Yeah, it's very easy to work with the MY process. Okay, see right away it is the expectation of mu, which is mu, plus expectation UT. Okay, the next ones, give you 0. Okay, because E UT minus 1 also 0. Okay. Next, variance YT. Variance YT. Okay, variance YT. Okay, after knowing the mean mu, the expectation of YT minus mu, YT minus mu, I get the UT plus next terms. Now I just need to take UT plus theta 1, UT minus 1, Q, UT minus Q, times the same thing. Q, UT minus Q. Okay, so what do you think? Which terms will give you 0? And which ones will stay there? Okay. So don't forget that UT is the wise noise process. So whenever, for example, when you multiply, you get UT, then you get the variance. Yeah, sigma. Okay. And how about UT and UT minus 1? Yeah, because all the auto covariance is equal to 0. Okay. Now, so what is left is only UT of sigma. Okay. Sigma, so we call it sigma U. I think it's sigma. Make it easy. Equal to sigma square, and then what's this? One for the first term. Okay, the next one, so UT and other terms will give you 0. Here, UT minus 1 with UT minus 1, we give you theta 1 squared. Okay, the next cost terms, all the cost terms are 0. Theta Q squared. Okay, that's it. Next, also covariance. And let's check gamma 1. So, gamma 1. If you know how to work with gamma 1, you can also work with the next gamma. Okay, what is it? This is the expectation. Which one you want? YT and Y t plus 1 or minus 1. Okay, expectation. Okay. YT minus the mean UT times now log 1 series. So whenever we have T, you replace with T minus 1. Okay. Or T plus 1. Okay, now theta 1. Theta Q, U T minus Q minus 1. Okay. Okay, so what is left? Okay, we can guess that we have sigma squared again as a common factor. So what is left inside the bracket? The case 1s is equal to 1. Okay, so UT can multiply by this one, give you 0 because you have a white noise on all this. Okay, with UT you give you 0. Okay, next UT minus 1 only multiply by UT minus 1 will give you something not 0. Okay, so I have a theta 1. Okay, theta 1 times the variance of UT, which is sigma squared. Okay, and the next terms. Next, you can imagine that here I have UT minus 2. Yeah, so theta 2, theta 1. Okay, and continue. That's the same. Yeah, that's correct. Yeah, theta 2, theta 1 is like theta 1, theta 2. How the last term? Last term. So minus Q, I think that we have something like here, right? And the one just before. Okay. So theta Q minus 1. Okay. That's it. Okay, Q minus 1. Just the last term there. Okay, and I can continue in case when s equal to 2, equal to 3, and so on. And finally, we get 0 for s greater than q. And gamma 2, gamma 3. Okay, and gamma s equal to 0 for s greater than q. Okay. You can imagine that there t minus s, suppose you have a t minus s minus 1, t minus s minus 1, and clearly here, okay, all the cross products will give us 0. Okay, because we have nothing in common between the two sum terms. Okay. So tau s equal to 0 for s greater than q. Consequently, yeah. So what's special? Okay, first of all, we see that expectation is a constant, variance also a constant, covariance constant for a given lag. Okay, depends on s. Okay, so it depends on s only, so it's a stationary process. So MAQ is stationary, quickly stationary, right? Okay, anything else? Gamma s equals to 0 for s greater than q, so tau s defined as gamma s divided by gamma 0, okay, equal to 0 for what? S greater than quarter q. Okay, which is one of the important features of the MA process, allowing you to recognize the MA process sometimes. Okay, here an example from the white noise. From the white noise, you see that from the white noise, you have UT and then UT minus 1. Okay, on the left, UT as well. Okay, with the constant, you can generate some examples of the MA series. Okay, the first one is a white noise process. Okay, here you have an example of the MA3 series. Okay, can you compare the two curves? Can you compare the two curves? Okay, the first one is the white noise. Okay, white noise. And then MA3. MA3 is, means that you give some numbers, right? For theta 1, theta 2, theta 3. Okay. Okay, plus this, you create the MA3 series. Okay, after imposing some coefficients, numbers. Why not? Okay, you can also give a number for mu. So, okay, anything special? Can you compare the two curves? What is the link between the two curves? From this white noise, you create this. Okay. You see that for the white noise, actually it changes values quite a lot, right? But the second series, MA series, is somehow smooth, right? So it's the feeling you have. Okay, do you have this feeling or not? See that the first one, okay, fluctuates quite a lot, but the second one looks smooth, smoother compare. This is a linear combination of the last values. Okay, okay. So when you take the sum, imagine that the next value, like here is the small, this one is large. You take the sum. Clearly, you get something in the middle. Okay, so moving average somehow will make the values more stable, I could say. Okay, so somehow it looks smoother. Yeah. Yeah, because later on, ARMA, maybe not only MA, but okay, you have also ARMA. ARMA is a combination of both AR and MA. Okay, now we go through each of them. Okay, so very often ARMA for the return, not for the stock price. Okay, the return. Why? Because the return will be stationary, Okay, so it's better to capture. Okay, compared to the price. The price then you should use because the price is not stationary, but the first difference will become stationary. Okay, so first difference is some very close to the return, right? So if you take the return, it's better. And each return also has a real meaning. Okay, real meaning, for example, 5% change, 3% change. Okay, so often we model the stock return or index return. Is that okay? Mm-hmm. Okay, can work very well. Okay. So understood. Okay, after getting MA3, okay, you can get it from there, and then you can check ICF. ICF 0, you get the number 1. Okay, tau 0 is 1. Tau 1 is here. Tau 2, tau 3. Tau 4, you see that is smaller than the blue line. Blue line, you have 2 blue lines corresponding to what? Can you guess what they are? When you use software very often, they can also give you the diagram like this. Remember, can you guess what is it? What are the blue lines? This one, that one? Yeah, confidence interval. Okay. So 0 plus minus. Okay, so it's 0 plus minus 1.96 divided by root t. Okay, so the 2 blue lines correspond to the plus and the minus sign. Okay, so whenever you get a value within the range, it means that it's not significant. Okay, not significant means tau equal to 0. Okay, of course you have the sample ACF, that's why, okay, it's not exactly 0, but it's somewhat small. Okay, so you said all these values stay within the range and they are not significant. Okay, supporting the fact that tau S is equal to 0 for S greater than Q. In this case, for S greater than 3. So we start with tau 4 is already 0, tau 5, so 6, and so on. Okay, they are all 0 or not significant. Okay, not significant because they have a sample autocorrelation. Okay, that's it. Okay, so somewhere when they run, okay, they give you the 2 lines like this, and then you can see right away whether the corresponding tau is significant or not. Okay. Okay, I think that MA2. So I think MA is quite easy to work with. It's sort of way to obtain the expectation and so on. So for this one, you can practice at home. Okay, maybe you take a break now, okay, because MA you take I think at least 10 minutes. So it's better to take a break now. Okay, for 10 minutes. Is that okay? Before we work with the AR model. Okay. So a break for 10 minutes. Yeah, why is that? I forgot. I don't know. Okay, maybe I forgot to share. Okay. Everybody all got the slide. Okay, MI2 process means that okay, you can practice at home, okay, with your homework. Okay, we write out exactly like this when Q is equal to 2. Okay, so a short break before continuing with the AR model. Let me stop.
Recording stopped. Recording in progress.
Okay, so now let's continue to to study the second family of the time series that are called the autoregressive models. Okay, denoted by AR. So we say that the series YT follows the autoregressive model order P. AR means autoregressive model order P, denoted by ARP when. Okay. Now it starts to be more interesting. Okay, you see, first of all, have constant, okay, as usual, and next, linear combination of lag YT, okay, from lag 1 to lag P. Okay, so now it's a linear combination of the lag YT, okay, the series itself, okay, plus the error term. Okay, when we can express YT the following way: constant mu plus linear combination with the coefficients phi. From phi 1, lag 1, YT minus 1, phi 2, lag 2, YT minus 2, up to phi b, lag b, so we get t minus b. Okay, and don't forget the error term plus ut. Okay, you can imagine that later on you can combine AR and MA. Okay, combine MA, then continue. Okay, some more terms. Linear combination of lag UT. Okay. Okay. So again, linear combination of lag YT and then error term, where UT is the white noise process with zero mean. UT equal to 0. Okay. Okay, for the variance we see later. Okay, for now on we have the variance UT. Okay, but often we call it sigma U squared. Okay. So this series is somehow more interesting. It's more interesting than the previous one. First of all, we can try to use the lag operator and transform this equation. So we use lag operator. You have used it before. L. What is the lag operator? L YT equal to lag 1 series. YT minus 1. Okay. So what does it mean? L squared YT. L squared here. Yeah, is L lag of, okay, L YT, okay. We can guess which is lag of YT minus 1, which is equal to YT minus 2. Okay. So L squared will give you the lag 2 series. Okay. Okay. And now we can use the lag operator to express transform the equation 1. And now we get okay, can play with that. Okay, in the right hand side you have mu plus phi 1. Okay, whenever we have the lag, we use L. L YT plus phi 2 squared L squared YT. And continue. Get phi P LP YT plus UT. Okay. So now we move on the terms with YT to left hand side. YT is here. Here, YT is the left hand side. Left hand side. Left hand side. Okay, what do we get? And now we get something YT. Okay, equal to the right hand side. What is left is mu. and ut. Okay, what is inside the brackets? Yt, first of all, we have 1 minus 1 L. Okay, so we're here 2 L squared. Okay. Last term will be 5B L B. Okay. So we count this phi L. We count this phi L. The big thing. So what is phi L? It's like operator, right? It's like a polynomial, you see? You see that here, okay, in practice, you have coefficients. You have coefficient 1.5, you have the coefficient 0.9, okay, 0.8, 0.7. Okay, so phi are the coefficients. Is that okay? So in practice, look at this. In terms of L, you have 1 minus 0.1 L minus 0.3 L squared is the polynomial. Polynomial in terms of L. Okay, polynomial of L. Okay, so at this level, okay, what do you want to do next? Any idea? Okay, what do you want to do next? What do you want to do next? Okay, intuitively. Okay, so now I get phi L. Okay, the big thing is what I call phi L. Yt equal to mu plus ut. Okay. And the question is, can you somehow move it to the right hand side or not? The question. So that's the question. I move it to the right hand side. Okay. Dividing, but is the operator. Okay, careful is the operator. Operator like L, right? And then you have something even more complex because you have polynomial of A. Okay. So it's not a number. Okay, when is the number then you can divide? Why is something like an operator? You have to take what? Just think about the easiest case matrix. You have to take the inverse of the matrix. Okay. But here, okay, don't forget that it's the operator in terms of L. Okay. Okay. But yes, inverse. But in terms of operator, then we can okay, we can think of phi L minus 1. Phi L minus 1. Phi L minus 1, which is 1 over phi L. Okay, how to write down. So 1 over. Okay. Okay, maybe I continue later. Okay, now let's take a look, all right, at the examples of the AR0. What is AR0? What do you think about AR0? Trying to see.
Mu plus.
Yeah, that's the, yeah. So we have nothing here, right? So mu plus ut. Okay, so this is a white noise. AR0 is simply a white noise process. Okay, AR1. Okay, we choose 5 because it's 0.3. We have the yellow curve, right? Okay, as an example, 0.9. Okay, the second example, the green curve. Okay, you see the values go up and down a bit more. Okay, compared to the case when phi is smaller, 0.3. Okay, the next case, AR2, phi equal to 0.3 or 0.3, and here bigger coefficients. Okay, and then you see that okay, it seems to fluctuate more. The second series compared to the blue one. Okay. Good. And now, okay, what interesting is the stationarity. Whether the series is stationary or not. Okay. Stationary or not. It's not easy, right? Not easy. Okay, that's why we try to expand from here. Yeah, so suppose that you are there after transforming the AR form. Okay, get this. Now I'd like to go further. Okay, go further. Okay, and in case phi L, remember there's a polynomial. Okay, have you ever seen something like this polynomial? I think that in the calculus class you have seen that. Okay, for any polynomial, like 1 divided by polynomial of x, x minus 1 minus 2 x minus 3. Okay, have you ever seen the way to decompose this? Okay, tell me how to decompose. Yes. Okay. Partial. I think that we call that. Yeah, right. Okay, somehow like this. Yeah. So basically, whenever you have something like this, you can always. Yeah, it's a very interesting result. Okay, you can always decompose this into a sum of 3 terms. Okay, here a constant. Okay, you can look for them. Okay, later on it is maybe 1/2 sometimes, 1/2, 1/3, whatever, minus 1. X minus 1 plus b divided by x minus 2 plus c divided by x minus 3. Okay, we call them partial. I think fractions. Partial fractions. Okay. Okay, when you have something like 1 over, okay, that one is more. Okay, that one is a bit different. Okay. Okay, for here, I think that I only need the first part. Okay, do you remember? We just because we talk about it. Okay, yeah. So again, we have a sum of 2 terms. Yes. So tell me what is the numerator? Yeah, right. Ax plus b under c. Yeah. Okay. Okay, you can always look for the coefficients ABC, so that this one can be decomposed. Okay. So again, using the same idea now, but now you look at the polynomial phi L. Phi L. You want to move to the right hand side, somehow you take the inverse, right? So it's like 1 divided by. Okay. But intuitively, because I tried to explain right here. It's like an algebra. Okay, with the proposed to investigate and see, right? See when the series is stationary. Okay, so suppose that now the polynomial, which is 1 minus phi 1, which is the polynomial phi L, okay, has exactly how many b, right? Because in the set of complex numbers, you know that any polynomial can be factorized in the set of complex numbers. And then in this case, so here's the equation 2. Okay, and then okay, from 2 now, I would like to continue with yt equal to somehow the inverse phi L minus 1. Okay, of mu plus ut. Okay. Okay, very often mu can be supposed to be equal to 0, because when it's 0, not 0, then you can take the series minus the mean. The mean rate for later. Okay, well, what is it? You can always factorize any polynomial in the set of complex numbers. So the idea is to see that now it's 1 over phi L, right? So I can multiply L minus, how to call them? Z1 maybe. L minus Z2. L minus Z, how many? B, right? Because you have a polynomial order B. Yeah, that's it. Times mu plus ut. Okay, and what's next? Okay, decompose here as a sum. Okay, 1 over L minus Zi. And I sum up over I. Is that okay? Is that correct?
A, B, C.
Okay, yeah, right. Okay, also coefficient. Okay, I can call it the C.
CI.
Okay. I. And I, okay, equals to 1, 2, 3. Yeah. Okay, and not finished yet. Not finished yet. Later on, I'd like to use something like this. Okay, remember 1 over 1 minus x. Okay, maybe, okay, if I ask you like this. Yeah, right. Yeah, x is smaller than 1 in absolute value. Okay, is what is the infinite sum? Okay, infinite sum. 1 plus x squared. Yeah, okay. Like 3 to infinity. Okay, so when when x absolute value is smaller than. Okay, so there's something that I'd like to use later. I'd like to see the form 1 minus L. Okay. Okay. Okay, we try to explain the ideas. Okay, to understand why actually you have this kind of condition for stationarity. Okay. Okay, now I like to see the form 1 minus something. Okay, so how to design? Okay, how to get it?
Divide both sides of L.
Okay, right. Okay, divided by L or by Z, which is the dividing by L. L is the operator. Okay. Okay, let's see. Okay, how about dividing by Z? Hình như phải dividing by Z, dividing by L không được. Được không? Có được không? Đúng rồi, phải. Oh, okay. Yeah, so we have to use either 1 minus, because I want to see 1 minus L something. Okay, we try. Okay, we try with minus that I first. Okay, okay, like this. So I divide this by minus that I as well. Okay, here I don't change it. Okay, so what do you think? We try. Yeah, we try, and then okay, numerator I call it AI because the numbers, right? The ZI are the where ZI are the characteristic roots. Okay, we call them, when you can decompose like this or factorize like this, we say that ZI are the characteristic roots of the polynomial phi L. Okay. Okay, so I try call this numerator AI and denominator what I get 1 minus L divided by I. Okay. Okay. Okay, I think that it could work like this already. And then again, multiply with something here. And then I want to see the infinite sum. Okay, next I want to see the infinite sum. Infinite sum from 1 to b, so I don't change it. Next, I want to see the infinite sum. Okay, because it's 1 minus this, so it's like L divided by ZI to the power of subscript k. Okay, when k goes from exactly like this 0 to infinity. Okay. Okay. Multiply by mu plus ut. Okay. In practice, mu can be supposed to be 0, and then what I get? Okay, to make it easier to see, suppose that mu is equal to 0. Okay, to simplify, and what I get? So L to the power of k ut is simply log k of u. Okay, like QU, and coefficient is simply now AI divided by ZI. Okay. Okay. Okay, and it works. It works. When or under what condition? So when the norm, right? Because here we have operator when the norm is smaller than 1. So maybe I need one more line. I clear. So this LK mu equal to 0. Okay, just to simplify, LK UT is simply UT minus K. Is that okay? Okay. Okay, and one of them is the index I from 1 to P. The next index is K from 0 to infinity. Is that okay? Okay. And in this expression, you see that if it works, then now because on the UT, what are the UT already? UT is exactly like the MA model. You see, it's the MA model with order infinity. Is that okay? Okay, MA model with order infinity. And you remember that MA model is stationary. Is that okay? So in case it works, then we get something stationary. Okay, that's the idea. Okay, to make the link between AR, you see the AR after transforming, and if it works well, I write out the condition later. If it works well, it's exactly the same as MA infinity model. Okay, so when it works well, like here, have the condition this to be smaller than 1. Okay, there. Why is the condition? Condition is at some point when I take this, okay, 1 minus this. You remember to get the infinite sum, and it works well when. Okay, when I take the norm, L divided by ZI, okay, the norm of L is equal to 1, okay, which is 1 over ZI. It should be smaller than 1. Okay, okay, you see? So it is the norm of L operator is 1. Okay, that's why. Why, okay.
Why L everything?
Okay, here is the norm. We talk about the norm, right? It's not a number, you see? Not a number. So you take the norm L divided by ZI. Norm L is equal to 1. Yeah.
So that's the condition.
Well, it's going to 1. Not definition, no, not definition, but okay, how to say it? Okay, L is like the linear operator or not? Okay, L is okay, L is the log 1 operator. Okay, we can also check. I think that we can also check that the norm of the log 1 operator is 1. Okay, something that we have to think about. Okay, why? Because L yt equal to yt minus 1. Is that okay? Okay, so maybe in linear algebra or something like this, or in okay, because for me I learned okay, a lot of different classes. Well, I don't know about you, but okay, operator L. In this case, it's linear, right? Linear. Okay, I think that we can prove that the norm is equal to 1. Is that okay? Okay, you can check and tell me later. So as your homework, try to make the link to other classes. Okay. Okay. Not always easy. Okay. So yeah, it works well. It works well when we have this smaller than 1. Okay, which much what you know before when absolute value. Of course, with numbers we only take absolute value, but here something more complex. Okay, smaller than 1. Okay, and then we get ZI on the characteristic roots. Okay, to be smaller than 1. Okay. Okay, so here I try to explain the main ideas. In the textbook, I think the previous versions of the book explain a little bit, but not this one, edition 4. They removed this part, but you can find it in the literature. Okay, just to support this result, okay, and to understand a little bit what is behind, okay, mainly about the operators, okay, how to transform, and then later on to check that if, right, if on the characteristic roots of the polynomial that I call Z1, Z2, Zp to have magnitude, right? Okay, magnitude greater than 1, because okay, most of the time you have the real numbers, but sometimes we also have the complex numbers. Okay, so absolute value or modulus to be greater than 1, then in this case you have a stationary process. Okay, so OER is not always stationary. It's stationary when on the characteristic roots of IL lie outside the unit circle, okay, with this to be smaller, bigger than 1. Yeah, so on the Zi to be greater than 1. Okay. Okay, so it works for real numbers and it also works for the complex numbers. Okay. Okay, so now, okay, we try to apply random walk. Okay, you all know about the random walk. Right? Random walk when the series yt is defined by this yt equal to yt minus 1 plus the error term. Okay, so stationary or not? Yes, no. Do we know if this one is stationary or not? Okay, first of all, it has the AR1 form. Okay, and now we know the way to check. Okay, random walk is stationary or not? Okay, why? Okay, now we know the way to check it, right? Okay, using the phi, okay, polynomial, and then you look for the characteristic roots. Okay, so the rule is there. Okay, if on the characteristic roots okay, lie outside the inner circle, then the series yt may be expressed as the MA series order infinity. And you all know that MA series is always stationary. Okay, and it works well under this condition. Yep. So when you transform, we need this condition for this to go well. Okay, now, of course, much easier to apply. Stationary or not, random walk. So example 1, random walk. Yt to yt minus 1 plus ut. White noise process is zero mean. Okay, so it has the AR form. Okay, first of all, I have to recognize the AR form or MA form. So it is the AR. Okay, one model. Okay, now we know how to check the stationarity of the AR model. Okay, how? Using lack operator. First of all, we transform yt here equal to L yt and move it to the left hand side, go to ut. Okay, and left hand side now is 1 minus L yt equal to ut. Okay, okay, and then what is phi L? Phi L is this operator. Okay, polynomial. Then you look for the roots of phi L. Okay. Now look for the roots of phi L. Okay. Roots of phi L, we also call them characteristic. Of phi L. Okay. How to get them? Yeah, you just solve the equation. The equation phi z equal to 0. Okay. So we know that phi L equal to 1 minus L, so phi Z equal to 1 minus Z. It's 0. Okay, so we get Z equal to 1. Okay, we get only one characteristic root, which is equal to 1. So it is outside unit circle or not? Outside unit circle or not? Yes or no? No. Okay, it's all the border equal to 1. So not outside the unit circle. So the series is not stationary. Okay. Okay, since okay, for it to stay outside the inner circle, okay, means that I have to check it for not right. It's equal or not greater. Is that better? I say, and since the one does not lie, okay, outside the unit circle. Unit circle. So in this case, you need all the roots to stay outside the circle. On series YT is not stationary. That okay? Not stationary. Okay. So for application, I think it's very easy. The way to transform it is much less. Second example. Now, first of all, is the AER model order 1 or 2 or 3. Example number 2. Okay, on the slide. Yes, YT 2 YT minus 1. Example. Okay, let's check the details on the slide. YT minus 3 plus UT. Okay. Hmm? 75. Okay. I guess first of all, I have to say whether it's a model AR or MA, okay, and which order. Okay, for the MA part, we have only UT, so okay, nothing special about MA. The AR, because you have a T minus 1, T minus 2, and T minus 3. So it is the AR model order 3. Okay, and then we transform using the linear operator or lag operator L. So now I move all the y and t terms to the left hand side. You get this. Okay, right hand side. You have a ut left. Okay, so 1 minus 2 L plus 2.75 L squared L3. Okay. Okay, which is equal to phi L. Yeah. Phi L. So now I like to check the roots of phi L. Yeah, by solving the equation. Okay, which equation? Phi z equal to 0. Okay. Phi z equal to this. So whenever you have the L, you replace with z. Okay, and then phi z equal to 0 means if we solve 1 minus 2 z plus 1 okay. Okay. Not always easy, but fortunately we have one obvious root, I think it will check with 1. 1, that would be 1 minus 2, so minus 1.
Number 3.
Number 3, 3 here. Okay.
No.
3 over there. Okay. 3 for the first number here. Three. Okay, so that's why you take this minus 1. Okay, hang on. 2. I guess 1, right? 1 is the obvious. Okay, root. So get the 3 roots z equal to 1 or z equal to I think 2/3 and 2. Okay. So now I have to check if all of them lie outside the unit circle or not. Okay, which ones lie outside the unit circle? Okay. Okay. This one, right, like outside the unit circle. Unit circle. Okay, but not this one. This one is smaller than 1. And 1 is equal to 1, so not lie outside the unit circle. Okay, so both of them do not lie outside the circle. So what is the conclusion? The series is not stationary. Series is not stationary. The AR series is not stationary. That's okay, because we need all the characteristic roots to stay outside the unit circle. That's okay. Okay, so now we got some idea about the stationarity of the AR series. The series is not always stationary. Okay, in case it is stationary, okay, do not because for the series to be stationary, we need. Okay, so the rule is there. We need all the roots to stay outside the inner circle. So in case you have only one of them, which doesn't lie outside the inner circle, then the series is not stationary. Is that okay? Okay. So it's enough to find one which is not bigger than 1. Okay. In absolute value. Because complex number is like the modulus. Okay, and in case when the series is stationary, you may wonder what is the way to calculate the expectation, the variance, covariance. Okay, leading to very interesting tools and also system, your Walker equations. Okay, that we need to use at some point. Okay, of course, it doesn't make sense. Okay, to calculate if the series is not stationary. Why? Not stationary means that maybe the mean is not constant, right? Variance is not constant, or covariance is not constant. But that's when this case cannot calculate. If the series is stationary, then you can go for it. You may wonder what is the unconditional mean, what is the variance, and what is the autocovariance. Okay. So the question now is, if the series is stationary, and what is the expectation? Okay, expectation also the unconditional mean. Sometimes you can see the textbook and literature. The variance, what is it? Okay, and also the tau. Okay. Okay, so is the series stationary? Which is the way to calculate this? Okay, for the AR is not as easy as the MA model. Okay, so first of all, I'm interested in the expectation. Okay, so since from the ARP model we have T y2, y3 minus 2, pi t, y3 minus 3, so like before, I like to take the expectation. And then we get expectation yt minus sign with mu, also expectation of yt minus 1. Also expectation of yt minus 2. Expectation of 1 minus expectation of okay. So what do you think? What do you think? Okay. From the equation, I take expectation of both sides. What do you get? Okay. Mu. Okay. How about this? How about that? Expectation yt minus 1. Yeah, they're equal. Yeah. Okay, so you see that that's why I have to say that. Okay, in case when the series is stationary, then we calculate the unconditional mean. Okay, so we call E yt because if the series is stationary, okay, equal to now okay, give it a name. I call it for example C. Okay. So it's also equal to expectation of yt minus 1. Okay, also equal to the other ones. Then I get the equation C equal to mu plus try 1 C to phi E C. Okay, and then I can move these terms to the left hand side. C will be equal to mu divided by 1 minus phi 1 minus phi 2 minus phi 3. Okay. Okay, so it's the way to get the mean or unconditional mean of the AR series when it is stationary. Okay. How the variance? For the variance, we try to use the same idea. Yeah. How the variance? Yeah, so now let's go B, right? The variance of yt when is the constant. The series stationary is also equal to variance of yt minus 1. Yeah, so on. Okay. Okay. Then we like to get an equation of B. Okay, so for that, I think that it is easier to suppose now that mu equal to 0. Okay. Suppose that mu equal to 0. Now we focus on suppose that mu equal to 0 just to simplify. Okay. For now, also suppose mu equal to 0 to simplify the way to write down. What is the variance? Variance yt, variance yt. Variance yt is the expectation and somehow the product. Okay. And okay, and I take the easier case b equal to 1. Just to simplify. Just simplify because you see that. Okay. If you know how to write out for b equal to 1, also know how to write out for b equal to 2, 3, or so on. Okay. So what is variance yt or variance yt? So mu equal to 0 is easier because my mean is 0. Okay, don't need to worry about anymore. Expectation okay, of yt squared. Yeah, that's correct. And then yt is equal to phi 1 yt 1 minus 1. Okay, yeah, that's correct. What choice? Now I want to replace yt here, yt here. Okay, write out the equation. Then yt equal to phi 1 yt minus 1 plus ut. That's not always easy to write down. Yeah, okay. I see. Now yt equal to that, I can replace phi 1 yt minus 1 plus ut times itself. Okay. What is see? I see that here. Okay, yt minus 1, I get the variance again. Okay. And first of all, I get find 1 squared variance y minus 1. Okay, which is the number b. Okay, that I try to look for. Yeah, so what is b? Basically, it's a little bit from b, and there I see b again. Okay, so what is left? This one and that one, this one and that one, I get ut. Okay, sigma u squared. Okay, now it's better to call it sigma u, but because sometimes have a sigma y, sometimes have a sigma u. Okay, ut here give you sigma squared. How about the cost product? What do you think? Okay, and yes, something like a 0. Maybe I write down first twice expectation. Phi 1. Okay, y t minus 1. Is that okay? Okay, you see, all right. Okay, and we know that y t minus 1. Y t minus 1 can now I use the equation one more time. It is okay, fine one, I move it outside. Okay, 1 second. Okay, it will be good to find 1 y t minus 2 plus ut minus 1. Okay, and I use this again now for y t minus 1. Yeah, they're right. So yeah, so this one and that one I give you 0. Yeah. Again, this one, okay, you continue, we get okay, always get 0. Okay, so you continue, and the lag will decrease somehow. Okay, so the second term I give you 0. That one. So in the end, okay, in this case, b as the variance will be equal to sigma u squared divided by, okay, I have a 1 here, phi 1 squared there. So 1 minus phi 1 squared. Okay, in case you have more terms, you can imagine that you have to add or minus phi 2 squared minus phi 3 squared, and you continue. Okay, in the numerator, you have sigma u squared. Okay. So this cost product to give you 0. And that's the idea. Okay, next, autocorrelation. Okay, fortunately, okay, we can obtain what we call the Walker equations system. Okay. Okay, now we try to get the system equations, and solving the system equation can get all the tau that we want. Okay, so the variance is fine. Right. Next, the tau. Autocorrelation coefficients. And next, I like to look for the tau. So I like to prove the Walker system of equations. Okay, let's check the first equation. Okay, let's check the first equation in the system. You see that is a system of how many? So the tau, we have a b, okay, unknown tau, okay, and also b equations. Okay, the phi we know them all. Okay, from the coefficients of the AR model. Okay, so basically you can solve this system and get the values of tau. That's okay. Okay, so let's prove the first equation. Equation 1. Let's get it. So it's the tau 1 and so on. Tau 1 obtained from gamma 1. Okay, so we start with gamma 1. Yes, autocorrelation. Yeah. Get lost now. True. Wow. Okay, so we start with gamma 1. Autocorrelation. Order 1. Okay, so by definition, it's the covariance of yt and y t minus 1. Is that okay? Okay, so of course we are supposed to simplify that mu is equal to 0. Okay, so I don't need to worry about the mean. And then the mean equal to 0. So what do you think? So the good way to write down would be to replace yt. Okay, yt because the mean is 0, but again, yt is okay, what is it? Constant 0 plus phi 1. Is that okay? Yt minus 1 plus phi 2, yt minus 2, phi b, yt minus b plus qt times what? Times yt minus 1. Okay, that's correct. Okay, I just replace the equation of yt. Okay, yt minus 1 is still there. Okay, I don't change it. So what do you get? What do you get next? Okay, now one by one to go. Okay, one by one. Here, yt minus 1, yt minus 1, you get variance, which is gamma 0. Okay, so I get phi 1, gamma 0. Okay, next. Yt minus 2 and yt minus 1, I get gamma. This one and that one. You get gamma. Yeah, gamma 1. That's correct. I get coefficient phi 2. Okay, so here the left-hand side is still gamma 1. Okay, and I continue. I finally get phi b. Yeah, it's a bit cold. 1 gamma. Yeah, minus 1. Thank you. Okay, so we almost get the first equation. So what is the next step? There I see only the tau. So I need to divide both sides by tau is obtained when you divide gamma by gamma 0. Okay, so we divide both sides by gamma 0. Okay. Divided by gamma 0, 0, 0. Yeah. So what I get? Yeah, now only the tau left. Yeah. Tau 1 equal to, here is 1, so phi 1 plus phi 2, tau 1, phi b, tau b minus 1. Is that okay? Which is exactly the first equation in your Walker system of equations. Is that okay? So we can check, right? Phi 1 and then tau 1, phi 2. Okay, phi p, tau p minus 1. Okay, using the same idea. Next, if you want to consider gamma 2, then you just write out yt minus 2. Okay, you get the second equation. That's okay. So the same way, for the next equations, you get a system of equations. Okay, for the tau. The p equations, okay, you can solve. Okay, we call the Ion Walker. Okay, system of equations. Okay. Again, it's a very interesting system. Okay, for many reasons. Later on, when you know about the PACF, yeah, not obvious, but if you understand it well enough, okay. From this one, you can also get a PACF. Anything else? Okay, just take one example. Easy example. P equal to 1. Okay, P equal to 1. Then your equation will be yt equal to phi 1, yt minus 1 plus ut. Again, this system will give you, okay, imagine the first equation will give you what? Okay, tau 1. Okay, it will still, okay, tau 1 equal to, from the first equation, phi 1, yeah, okay. Okay, because in the model you have only phi 1, we don't have phi 2, right? Yeah. Okay, and so also phi tau 2. Okay. Okay. Okay, then if you look at the second equation. Okay, second equation, and of course this part will disappear from here, right? Tau 1 times pi 1. Tau 1 by 1. Okay, and now the tau 1 is equal to pi 1 already, so it is pi 1 squared. Is that okay? So that's it. Then the next equation will give you, I think it's somehow the same. Pi 1 to about 3.
So when
Okay.
when I less than 1 is good,
Yeah, okay, yeah, that's correct. Yeah, so get the numbers easily, right? Okay. Okay. So it's a way, right, to calculate first of all the expectation, the variance, and the autopopulation of the AER process when it is stationary. Okay. So it's not obvious, okay, compared to the MA model, because the MA model is always stationary, so it's very easy to get. Okay. So I think that we, I think this example is exactly what I wrote out before. So you can check that again. So I think that, okay, we continue on the next week. Okay, I am now quiz.
quiz.
No, your homework.
Em hình như là
Đôi lúc là học xong sớm thì làm trên lớp nhưng mà khó là thời gian trên lớp. Ok, gonna check 10 or something. Check 10 or something. Sớm muộn phải làm thôi, nhưng tóm lại là giờ đi coi như là học. Tóm lại là có chưa gặp trên được không? Thôi muộn rồi đúng không? Ok, còn cứ bản nào thì cứ lại con. Ok thôi một rồi thôi. Ok không.